Welcome to the fascinating world of quantum cryptography. Today, we will explore how quantum mechanics is revolutionizing the field of cryptography and what this means for the security of our digital communications. Classical cryptography relies on the assumption that certain mathematical problems are computationally infeasible to solve with today's computers. RSA, for example, is based on the difficulty of factoring large numbers. Elliptic curve cryptography, or ECC, depends on the hardness of the discrete logarithm problem. But, these assumptions begin to fall apart in the presence of quantum computers. Quantum computing introduces a fundamental shift. Using principles of superposition and entanglement, quantum algorithms can solve some problems exponentially faster than classical methods. The most famous example is Shor's algorithm, which can factor integers and compute discrete logarithms in polynomial time, effectively breaking RSA and ECC. A sufficiently powerful quantum computer could render most public key crypto systems obsolete. For symmetric cryptography, the threat is less severe, but still significant. Grover's algorithm provides a quadratic speed-up for brute force attacks, meaning that a 128-bit symmetric key, like AES-128, offers only 64 bits of effective security against a quantum adversary. To mitigate this, increasing key lengths to AES-256 is recommended, which would still require 2 to the power of 128 operations, considered quantum safe for the foreseeable future. Quantum threats are not theoretical anymore. Although today's quantum computers are far from being able to run Shor's algorithm on RSA 2048 at scale, progress is accelerating. Nations and tech companies are investing heavily in quantum hardware. Researchers estimate that within a few decades, or possibly sooner, we might see quantum machines capable of breaking widely used cryptography. Post-Quantum Cryptography and Future Strategies. This looming threat has led to the emergence of Post-Quantum Cryptography, or PQC. These are cryptographic algorithms designed to be secure against quantum attacks, but still executable on classical hardware. Leading candidates include lattice-based schemes, hash-based signatures, code-based cryptography, and multivariate polynomial systems. In response, the U.S. National Institute of Standards and Technology, or NIST, initiated a global competition to standardize post-quantum algorithms. As of now, finalists have been selected, including schemes like Kyber for encryption and dilithium for digital signatures. These will likely replace RSA and ECC in the near future. Transitioning to quantum-resistant systems poses major challenges. Legacy infrastructure, embedded systems, and long-lived certificates cannot be replaced overnight. Hybrid approaches, combining classical and post-quantum algorithms, are being tested as interim solutions. Additionally, cryptographic agility, the ability to switch algorithms without redesigning the system, is becoming an essential design principle. The quantum era doesn't mean the end of cryptography, but it does require a paradigm shift. Organizations must begin inventorying their cryptographic dependencies, evaluating risks, and planning migration strategies. Governments and industries that act now will be best positioned to protect their data in the quantum future.